Hi, I'm Carl, and in this video we're going to have a look at questions 29 to 33 of section 3 of the orange booklet. So this is a pretty complex question about different reduction potentials. We're given a table here which I've copied out, and we've been told what the standard reduction potential, or E, is. Finally, we're told that a positive reduction potential represents a system that is more easily reduced or gains electrons than hydrogen. The way I think of it, it's the strength with which they would want to steal electrons. It's their ability to steal electrons. I think that's an easier way to think of it. So question 29 says, which one of the following will take place if bromine is added to a solution that contains chloride and iodide ions? So we've got bromide here, chloride and iodide. So really we're just going to be comparing these three different outcomes. So remember that oxidation is going to be the loss of an electron, and reduction is going to be the gain of an electron. Now we're going to be comparing these three different E values to see what's going to happen. So as I said, this E value is really just a measure of how easily something can steal electrons. As we can see, bromine has a higher E value than iodine. And if iodide ions and bromide ions are present, or bromine is present with iodide ions, then iodine will be oxidized. And the reason for this is that we're going to be essentially doing the reverse of this reaction here. It's going to be stealing the electrons off the ions here and then producing these bromide ions. So we would get this reaction happening. These two electrons will go onto the bromine and you get two bromide ions here. This will be oxidation of the iodide ions, or reduction of the bromide ions. But what about the chloride ions? Well, as we can see here, the chloride ions have a higher E value than bromine, but not as much as how bromine has a higher E value than iodine. So that means that will chlorine then go on and steal the electrons off the bromide ions that are produced here? Well, no, because we're told that the solution contains chloride ions. They couldn't steal any more, so chloride ions aren't going to do anything here. The only change is going to be the bromine stealing the electrons off the iodide ions. That would be oxidizing them. So the answer for number 29 is going to be B. If we look at 30 then, it says which one of the following species would reduce a solution of hydrogen ions to hydrogen? So again, we just want to compare these different values here. If we're going to be reducing a solution, we're going to be providing some electrons here. In other words, which one of these three substances, iodine, copper and zinc, could hydrogen steal these electrons off? Now remember, this E value is its ability to steal these electrons. So we're going to be looking with these three options to see which E value it does, or has a lower, or which substance here has a lower E value than hydrogen, because that means it has less of an ability to hold on to its electrons here. So if we're looking at iodide or iodine here, it's got a higher E value than hydrogen, and so it would want to steal the electrons off hydrogen instead of provide them for the reduction, so it's not going to be iodine. If we look at copper, the same is true. It's got a higher E value. But if we look at zinc, it's got a lower E value, which means that hydrogen has a greater ability to steal these electrons and reduce itself, which means that the only substance that would be able to reduce hydrogen ions to hydrogen is going to be zinc, or this is going to be 3 only, meaning the answer for number 30 is going to be C. If we look at our next question, then this is question 31, and we're given another table with some half reactions. Question 31 says, based on this table, which one is the strongest reducing agent? Okay, so this E value crops up again, and if it's something's ability to steal hydrogens, it's its ability to oxidize something else. You know, if you're going to be taking electrons of something else, you're going to be oxidizing it. So the strongest oxidizing agent will have the highest E value, but the substances with the lowest E value then would be the strongest reducing agent. And looking at this table, we can see it's the bottom one here. And so that would give us an answer of D for number 31. 32 then gives us an equation. And this is where it gets a little bit complicated because we have some maths to do. We're told that N is the number of moles of electrons transferred in this reaction. And we're asked to find the value of K for this. So I think first of all, it'd probably be worth working out how many moles of electrons is transferred. And we're actually just going to be looking at our table here. This is essentially the reaction that's happening, only in reverse. And we're moving 2 moles of electrons in this reaction. So that means that N is going to be 2 for this. So we can start plugging in our numbers and see where we get. So we know that the value for the E cell is going to be 1.02. And this can be 0.06 over 2 moles of electrons, which is moved. It's going to be multiplied by log to the base 10 of our value of Q that we're trying to find. Okay, well then we can try and simplify this. We can multiply both sides by 2 and we get 2.04. We can divide by 0.06 and then we get this line. If we were to simplify this equation, that's the same as 204 over 6, which is 102 over 3, which is going to be 34. Yeah, so then we have our expression 34 equals log to the base 10 of KEQ. Now that's one of the answers, 34 is one of the answers, but we're not done yet. We need to find KEQ. So remembering our log rules, KEQ then is going to be equal to 10 to the power of 34. And that gives us an answer of D for this question. And then finally we've got question 33 and we've got some more numbers to deal with here. We're told that we're given the magnitudes but not the signs of some standard electrode potentials of these 2 organic molecules M and N. And then we're given some more information. So we're told that whenever 2 half cells containing M and N are connected, electrons flow from M to N. So remember, electrons are negatively charged. If they're flowing towards N, then that means M is going to be less positive or more negative than N. And now we're told this because we can see that 0.26 is obviously smaller than the 0.34, but we don't know the signs. And the next sentence gives us some more information about this. So we're told when M is connected to a standard electron, the hydrogen electrode, electrons flow from the N half cells to the standard hydrogen electrode. Now the standard hydrogen electrode has an electrode potential of 0, and we can get this actually from table 1, where we're told that the E value for the reduction of hydrogen ions is 0. But it might just be worth the SHE is going to have an electrode potential of 0. Now, what does this mean? If we've got electrons moving from M to the hydrogen electrode, that means M has to be more negative than the hydrogen electrode, right? So if the electrons are being pushed towards the more positive thing, and they're moving away from the more negative thing, they're moving away from M, that tells us actually this is going to be negative 0.26 volts for its electrode potential. And that tells us also this has to be positive 0.26 or 0.34 volts. Okay, so then we're told what would the potential of a cell made up from these 2 half cells be? So it's actually just going to be the difference. It would be the electrode potentials, the difference between them. So we want to take them away from each other. So we've got 0.34 and we want to take away negative 0.26. And that gives us an answer of positive 0.6 volts. And that is answer A then. So number 33 is going to be A. So those are some pretty complicated chemistry questions. I hope that helped. Thanks for watching.